Yes, good afternoon.
Good afternoon, sir.
Yes. So, uh, yesterday we started with the module 2 and we went through the data processing instructions. And in that, we discussed this move and move n. And with this example, this was an example for move instruction. So, a simple example which you already know. And this is the example for embedding a condition within the move instruction. Okay. We are embedding the equality condition inside the move instruction. So the value of R1 gets moved to the register R0 only if the zero flag is set. Only if the zero flag is set, so then the content of register R1 will be moved into the register R0. So this is the condition flag. Sorry, condition embedded inside the move instruction. So I think I showed you this example. Okay. So this example is done already. So we have taken the value of R0 as 5 here and R1 as 6. Now I'm trying to subtract 4 from 5. So now R0 will be a non-zero value. The value of R0 is non-zero value. So now we don't have the zero flag set. And I'm checking the condition here, move EQ R2, R1. Since the zero flag is not set, so this will not get executed. Okay, it will ignore the execution of this statement. And in the another instance, what I did, I made the changes to the program. I made it as 4, and then I executed it once again. So 4 minus 4, 0, and the value in the destination register R0 is also 0. Since I've used sub s, the suffix s is used, it updates the conditional flag. Since the value of R0 is 0 now, 0 flag will be set to 1. So is set to 1, and this move EQ examines the 0 flag. Since it is set, now it will go for moving the value of register R1 to R2. So this is what the execution we did in the previous class. So now we'll continue our discussion. Okay. Now here again, move s, for move also you can add the suffix s. Okay. So when you add the suffix s, again the move instruction also can update what the conditional flags. Okay, the conditional flags can also be set by using the move instruction if you add the suffix s to it. Now again we have the suffix s added here, and there is no condition. So we don't have the condition here. So we have the suffix s. Now when I'm moving, this can be either immediate number or it can be a register. Now when I'm moving that to the destination register, if the value that gets loaded into the register RD is 0, then again we have the 0 flag set. Okay. So if this is not, this is a non-zero value, so then the 0 flag remains 0 itself. So adding the suffix s is possible for the move instruction also. Now here you understood how to embed a condition inside the move instruction. Now here you understood how to add the suffix s to the move instruction in order to update the conditional flags. Now I have an example on this. Okay. Uh, Again, in the register R0, I'm taking the value 0. In the register R1, I'm taking the value 1. Now here, I'm just saying move s, the suffix s is added, and move s R2, R0. So value of R0 is 0. Now what I'm trying to move to the register R2 is 0. Now since I'm moving the R2 value as 0, now this s suffix which I've added to move instruction, it will set the 0 flag. So you can see Z is written in uppercase here. That means the 0 flag will be set. So very next statement, what I'm doing, R1, R3 I'm writing. So R1 is 6, and that is what I'm trying to move it to the register R3. Now R3 gets the value 6, which is a non-zero value, and this is the most recent instruction which is performed right now. Okay, prior to this, this was the most recent, and since the suffix s is added, it updated the 0 flag to 1, and it is written in uppercase. Now here, so the next one, the most recent one to execute is this, and it is moving the value 6 to the register R3, which is a non-zero value. Now since we have the suffix s here also, what it will do, it will bring the value of 0 flag from 1 to 0. So now this is written in lowercase. You can see this is bigger in size and this is smaller in size. Okay, so it will bring back the 0 flag to 0 since the value in the register R3 is a non-zero value, because this is the most recent operation that is performed by the ALU. Now we'll quickly execute this. I'll copy this. Okay, let me open new project. Okay, let me give it a sample 4. Okay, sample 3 is not there. Let me give it a sample 3. See, copy all these things, and after finishing your lab programs, you can, if you have time, you can do these things. Sample 3. The project name also, I'll give it as sample MPLE sample 3. Now I save my program inside sample 3 as sample 3. I've copied it already. I'm pasting it. I'm not writing it from the beginning. Okay, let us save the time. So now I'll add this to the source group 1. Translate, build, and then debug. Okay, now we'll start. Say R0, I'm loading with the value 0. R0 was already 0. Now again it is made as 0. Now R1, I'm loading with 6. So R1 got the value 6. Okay. Now I'm saying move as R2 comma R0. R0 value is 0. Now what is getting loaded into the register R2 is 0. Now the 0 flag should be set. Okay. Since I've used the suffix s for the move instruction. Now I press F11 now, you can just observe now the 0 flag will be set. So 0 flag is set. Okay. In the next statement, what I am moving to the destination register R3 is the value of R1, that is 6. Now again, the 0 flag will be put back to 0. So 0 flag has become 0. So this instruction sets the 0 flag and this instruction resets the 0 flag. So hope you understood. Is that clear?
Yes, sir.
Yes, sir.
Now we'll go to the next thing. Now barrel shifter. So as I was mentioning, one of the ALU input is connected with the barrel shifter, and majority of the instructions can take the benefit of the barrel shifter to perform the complex operations. And can move instruction take the benefit of the barrel shifter? Yes, even move can also go for using the barrel shifter. Say when you're moving some value from one register to the another register, and I don't want to move the content of the source register as it is into the destination register. So the examples what we discussed till now on move. So what we were doing, we were moving the content of source register as it is into the destination register. Now before moving the content of source register into the destination register, if I got to do some kind of a processing, say left shifting or right shifting, I can do that, and then I can go for moving the result after shifting operation to the destination register. So that is what we're going to learn now next. Okay. So move instruction, in move instruction, n is a simple register or an immediate value. Okay, so that you already know. And now it can also be a register RM that has been pre-processed by the barrel shifter prior to being used by the data processing instruction. Now this RM, the register RM, it can also be what pre-processed by using a barrel shifter. And there's an unique and powerful feature of ARM processor is that its ability to shift the 32-bit binary pattern in one of the source register left or right by the specified number of positions before it enters into the ALU. So this you can do. You can go for performing either the left shift or the right shift by the specified number of positions before the data gets into the ALU. Okay, and then this flexibility, the shift increases the power and flexibility of many data processing operations. So, but yeah, you can use this ALU facility in the move instruction, but there are certain instruction where, sorry, you can use this barrel shifter facility or shifting facility even in move instruction also. But there are certain instruction where instructions that do not use the barrel shift. As I already mentioned to you people, one is multiply because the architecture MAC is completely separate. So and the MAC is not connected with the barrel shifter. Multiply is one such instruction, and CLZ is another instruction. Count leading zeros, and later we'll be using this instruction CLZ instruction. And Q add is one more. Sign saturated 32-bit addition. This is and we are not going to use this instruction anywhere. So these are few instructions which do not make use of the barrel shift. Okay, barrel shifter is not available for these instructions because all these three instructions they get processed inside the MAC, and for that reason, so the barrel shift is not available for these things, and it is not possible for you to perform shift or the left shift or right shift when you people are executing these instructions. Now we understood that yeah, move, you can move uses the barrel shifter, or move can take benefit of the barrel shifter. Now how do I do it? Say this is the example which I'm taking. Say R5 I'm taking the value 5 and R7 I'm taking the value 8. Now this is what the precondition I'm assuming. So in R5 I have 5 and R7 I have 8. Now I'm writing this statement move R7. R7 is my destination register. R5 is my source register. In my source register right now I have the value 5. Okay. Now on the value that is present inside the register R5, I need to perform logical shift left. Logical shift left. There are two things. When I'm saying shifting, there are two shifts. One is logical shift and arithmetic shift. So soon you'll get to know those things. What is a logical shift is and what is an arithmetic shift is. Now what I'm trying to do now is on the value which is present inside the register R5, I'm trying to perform logical shift left by how many positions? Two positions or two times. Logical shift left two times. Shift the bits left how many times? Two times. So this is what I have here. So now R7, what it is going to get the destination register, it is something like this. So take the content of the register R5, that is 5 into 4. Okay, since you're shifting it two times, let me take a pen. So 5 is the value. Okay, now how 5 is written in binary? So strictly speaking, you got to write it using 32 bits because when you assign this 5 to the register R5, it gets sign extended to 32 bits. Let me write 32 bits. 0, 0, 0, 0. So the first 0, 0, 0, 0, 0. The second 0, 0, 0, 0, 0. The third 0, 0, 0, 0, 0. The fourth 0. And then similarly 0, 0, 0, 0. Fifth 0, 0, 0, 0, 0. Sixth 0, 0, 0, 0. Seventh 0. And now 0, 1, 0, 1. This is 5. Now in other words, so if I'm writing it in hexadecimal, it is something like this. 0x, sorry, 0x, what it is? This is 0 and this is again 0. Sorry. So 7 zeros, 1, 2, 3, 4, 5, 6, 7, and a 5. It is something like this. Okay, this 0 corresponds to this, and this 0, this, 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 and this is this, and 5 is this. Okay, now if you perform 2-bit left shift, then what is the result you'll get? So 2-bit left shift on this. Okay, so these 2 bits will go outside. Okay, a left shift. This bit will come. This will go out. This will go out, and this 0 will come to this position. So 0, 0. So what I'm writing? This 0 is here. This 0 is here, and this 0 comes here now. 0, 0. This 0 comes. And similarly, like this, it happens. 0, 0. Okay, now and finally let me write here. So this 0 will come here. Okay, here 0, 1, 0. So this 0, 1 will come here, and this 0, 1 will come here, and you have 2 zeros introduced here. Okay, it is something like this. Okay, how much is this now? So if I complete, so this is 4. Okay, and what about this? It is 1, 4. Hope people are following. Hello.
Yes, sir.
See, I'm not writing it full. So it is something, and this component, it becomes now 0, 0, 0, 1, and the rest all is 0. So it is something like 6 zeros here. 1, 2, 3, 4, 5, 6, and it is 14. So 14 in hexa. Correct, right? And this is nothing but what right now? 20. Hope people are following. 20 in decimal. Got it?
Yes, sir.
Okay. So shifted left, we are getting this. Now this is nothing but, so whenever you shift 2 times, so on what you're shifting 2 times, on 5 you're shifting 2 times. Okay, it is something like this. In general, 5 into 2 to the power number of bits shifted, number of bits shifted. Number of bits shifted. So that is 5 into, in this case, how many are shifted? How many bits? How many times we are shifting? 2. 2 to the power 2. So that is equal to 5 into 4. That is nothing but 20. 20 in hexadecimal is how much? It is 14. So okay, people understood?
Yes,
Yes,
sir.
sir.
Okay. So this is the example. So now, and if I ask you a question, okay, and this is the value, 14 is the value that gets loaded, that gets moved to the register R7. Now what will be the value in R5? Is it still 5 or is it 14 here also? It is 5 here. So the post condition you can see here. Only R7 gets the value 20 or hexadecimal 14. Okay, the destination register, but in R5 it is still the same old value, that is 5. So clear, right? Clear, right? Now instead of 2-bit left shift, if I do 3-bit left shift, what is the value you should get? So 5 into 2 raised to 3, how much it is? 8. 5 into 8, so you should get it as 40. Have you understood? Hello.
Yes, sir.
Okay. So with this, okay, we'll come to this. So barrel shifter operations. What are the operations that you can do? So these are all the things that you can do. So logical shift left. It's called as logical shift left. And how do you do that? So something like this. So this is the X represents the register here. Okay, the registers whose content you need to logical shift left, and this Y says how many are bits are the shift amount. Okay, and then similarly LSR is logical shift right. X is the register whose content that should be shifted towards the right, and what is the shift amount. So this shifts left and this shifts right. And then ASR. So this is arithmetic right shift. Now, when I say arithmetic right shift, see the sign bit should not be affected. So I said the most significant bit, that the 31st bit is what? The sign bit. And it says if it is 1, so it is a negative number. If it is 0, it is a positive number. Now, this sign bit you should not modify. You got to preserve the sign bit as it is. Okay. By preserving the sign bit, you're going to shift it towards the right. That means sign bit stays there only. The 31st bit position, we're not going to affect it. So from the 30th position onwards, we keep shifting it. So that is what is arithmetic shift right. And then we have one more called as rotate right. So here when you did the logical shift left or the logical shift right, when you're doing, what is happening? See, when I'm shifting left, so say 2 times I'm shifting, these 2 bits will go out. That means I'm losing these 2 bits permanently. And what happens? So we have 2 zeros added from the right side. Okay, so no matter whether the bit that goes out of the register here is 0 or 1, what gets inserted from the right hand side is zeros. Okay, people are following what I'm saying?
Yes, sir.
Okay. Now rotate right, what happens? Instead of losing the bits, so the when I'm shifting it rotate right or rotate left, say I'm doing rotate left, so the bit which is there in the MSB position, okay, so it'll be shifted towards the LSB. So it's some circular it is. So this bit comes here, this bit comes here, this bit comes here, this bit comes here, something like this, and finally this bit comes and sits here. So MSB bit will come and take the position as the lowest B bit. Okay, that is what is rotate left. And similarly, you can also do rotate right. When I say rotate right, it is something like this. So this bit comes here, this bit comes here, this bit comes here, and the bit which you're seeing in the LSB position. Okay, so what happens? It comes and sits at the MSB position. That is what is rotate right. And then there is something called as RRX also. Rotate sign extended. Okay, so it's rotate right extended. Now all these four LSL, LSR, ASR, ROR. So how many bits maximum they can rotate? They can rotate 32 bits because 0 to 31 is the capacity and total comes to 32 bits. But this RRX can go for rotating up to 33 bits, not 32, 33 bits. And this also includes where is that another bit coming from? That bit is the carry flag. So in the conditional flags, there was a carry flag, C flag. Now even that also it includes. So including the carry flag, it rotates. Now it comes to around, so 33 bits. Okay, so 30, the maximum shift that you can do using RRX is 33 bit shift. But all these three, the maximum shift that you can do is 32 bit shift. Hope people are following.
Yes, sir.
So this includes the carry flag also. So next slides you'll understand. Okay, and this is a typical example how the shifting is happening. Okay, what we are doing now is a logical shift left by 1 bit we are doing. So this is the original content as I wrote here. It is the same thing, but I wrote it not looking nice, but this is looking nice. So this is the value which I've taken. Okay, so 8 and all the bits are not shown here. So because I was interested in 8, so 1 0 0 and here one more 0 is there. Okay, 8 it is, and then 4 I have taken, and the rest all I have put dot dash dash dash. Now how you are shifting? See, something like this. This 0 comes to this position, this 0 comes here, and what happens to this 31st, the bit which is there in the 31st bit position? So it goes to the carry flag. So, and since the bit value is 1, so the carry flag is 1. Are you understanding this? So initially the condition flags were something like this: N, Z, C, V, and that Q we don't take into account. That is not required for us. So these are the condition backs or flags it is. I don't know, by mistake is written it as backs or flags, and even you can also call it as black backs, no issues. So N, Z, C, V, and Z is in lowercase. Sorry, C is in lowercase. Now when I'm performing logical left shift by 1 bit, this I said this will go out of the register. This will go out of the register where it is with this value is present, and out of the register it will go, I said, but where it will go? It goes and sits inside the carry flag. So now since the bit value that is shifted out is 1, so the carry flag is set to 1. Say for assume the bit value at the position 31st position is 0, and if that goes out, what will be the carry flag? Carry flag will be 0. So this I need to write it as in lowercase. Okay, people understood? Hello. Please unmute and speak. Say if I'm writing move something like this, move S. So every time, and I'm say R7 and then R5, and then I'm writing LSL 1. Assume in R5 I have this value. I have this value. Now if I assume this is the value that is there in R5, what gets out of the register is 1, the bit 1. Okay. Now since the suffix S is also added, so it goes and sits inside the carry flag, and the carry flag is set to 1. Is it clear? Hello.
Yes, sir.
Yes,
Okay.
sir.
So next, and this is the result what you get. Okay. Now, so you can just ask me, sir, this is 80004 and this is 0008. How is that possible? See, but when I write this, the most significant bit, what is the value? 1. That means it's a negative number. It's a negative number. And what about this? It's a positive number, which is much bigger than this. Hope you understood. Hello.
Yes, sir.
Okay. Next. Now barrel shifter, left shift, how it happens. Shift left by specified amount, and when you're shifting, so it is something like multiplies by power of 2. Say for example, if I say shift logic perform logical shift left by 5 bits, okay, so it will give the effect of multiplying the number by 32, because 2 raised to 5, because shift amount is 5 now, 2 raised to 5 is nothing but 32. So it gives the effect of multiplying a number by what? 32. Hope you people understood? Yes or no?
Yes, sir.
Hello.
Yes, sir.
Okay. Next, so when you're shifting it left, so the bits which are there at the MSB position, so the moment they go out of the register, so they get into the carry flag, and we have the zeros introduced are added from the right hand side. So if so 2 zeros or 2 ones goes, say for example 2 ones goes out of this register, okay, now 2 zeros gets added. So no matter what goes out of the what register, whether it is a 0 or 1, but what gets added from the right hand side is the zeros. Okay, don't confuse. So if the bit value is 1 and if the when 1 goes out of the register, it's not like you should add 1 here. Okay, so whatever goes, whether 0 or 1, gets shifted out of the register. What gets introduced from the right side is the zeros. Okay, and the value on the bit which goes out of the register is moved into the carry flag. Next, logical shift right again. So this gives the effect of multiplying the number by, okay, 2 to the power shift amount. But this, when I say shift right, it gives the effect of dividing a number by 2 to the power shift amount. Say logical shift right I'm doing, okay, so for 5 times, so 2 raised to 5 is nothing but again 32. Say I'm trying to perform so 5-bit right shift on the number, say 100. So on this value, I'm trying to perform 5-bit right shift. Now what it gives the effect of dividing this 100 by 2 raised to 5, that is nothing but 32. When you're multiplying, so sorry, when you are shifting left, it gives the effect of multiplying the number by 2 to the power so many things, so many shift amount. And this you can observe here when you're doing logical shift right, so the bits will get out of the register from the right hand side, and whatever gets out of the register from the right hand side gets into the carry flag, and we have the zeros added from the left hand side. Is it clear? Yes. Hello, please unmute and speak.
So shift right also will go to carry flag.
Yes, it goes to the carry flag. Even when you're doing shift right or shift left, if you're using the yes suffix yes, it goes. Is that clear?
Yes, sir.
Okay. Next, arithmetic shift right. Now everything is same. Only thing is, now when I say arithmetic shift right, the sign bit must be preserved. Okay. See, preserves the sign bit. So you cannot shift the sign bit. If you are shifting the sign bit, then the value, you know, what we say, the polarity of the value itself will change. Okay. So the positive becomes negative and negative becomes positive. So the sign bit should not be changed. The sign bit should stay there only. Every time you're shifting, say what we are doing now, shifting right. So the bit that gets shifted out, okay, from the right hand side gets into the carry flag, and when say when all the bits get shifted, so what I do now, this say sign bit, this bit is 1. Instead of shifting this here, okay, and pushing 0 to this place, what I do now, I shift this bit here itself. It keeps rotating there itself. That means this bit will be always 1. And what gets, so and all the bits from here to here, they get shifted. And say for example this bit is 1, it gets shifted to the next position, and what comes to this position is 0. So that means the sign bit is preserved. So when I'm doing ASR, it preserves the sign bit and shift the rest all. Hope you understood.
Yes, sir.
Okay. Next, rotate right. So this is again, you can see rotate right and rotate left also you can do. Okay. You can, if you just observe here, since I'm saying rotate right, okay, so the bit that gets out from the LSB position gets into the carry flag, and the copy of the same bit is also rotated back to the MSB position, or sent back to the MSB position. Okay, is this clear?
Yes, sir.
The bit one get shifted out from the right is sent to the carry flag, and a copy of that is also sent back to the MSB position. Okay, so 2 times if you do, so first time when you're shifting right, so the first bit, the bit which is there at the 0th position, gets into the carry flag, and it comes and sits in the 31st position. So if and next again one more right rotate if you're doing, so the next bit goes here, the next bit which is there at the LSB position goes to the carry flag, and the same a copy of that is sent back to the 31st. So it is something like a cycle, but a copy of that is also sent to the carry flag. Now rotate right extended, RRX. Okay, I said so all this can, maximum number of shifts that they can do is 32-bit, but this operation uses CPSR C flag, that is carry flag, as a 33rd bit. So the maximum number of shifts that you can do here is 33 shifts. Okay, so just including this. Okay, so this is 32 bit. This is 32 bit, and this is one more bit. Okay, now when I'm say shifting right, rotate right through carry it is. Okay, so what happens now? So the bit here at the LSB position of the register goes to the carry flag, and the bit which is here in the carry flag is shifted back to this. So now totally 33 bit shift what we are doing here. The maximum that number of shifts that you can do here is 33 bit shift. That is including the carry flag. Now we have the example here on MOVs along with the barrel shifter. Okay. Now this is what the precondition I'm assuming here. Now CPSR is this. So if you just observe now, except this fast interrupt, so none of the other flags are set. Okay, and it is in the user mode. Next, R0 is this is the value that I'm taking, and R1 this is the value that I'm taking. Okay, this is before execution of move. This is the status. Now the move is getting executed. Move is R0. I'm writing this is my destination register now. R1 is this, and what I'm doing is logical shift left by 1 bit. Okay. Now you can do this now. So if I do the logical left shift on this, so what is the value I should get in R0 is this. Okay, and you have the carry flag shown as 1. Why? Because in the MSB position, since this is 8 is written as 1 0 0 0. This is the bit value at the 31st bit position is 1, and this is what gets into the carry flag. Since the carry flag is set right now, so it is shown in uppercase, and this is same as we did here. This one. Hope you understood.
Yes, sir.
Okay. Okay, this is the example now. Now barrel shift operation syntax for data processing instruction. So you can also give immediate number. Okay. So immediate how to write, you know, so it is something like this. And if it is a register, we write it something like this. So logical shift left by immediate. Okay. So RM, LSL, this is immediate. And all the examples what we discussed till now was immediate. So because the shift amount was specified as an immediate number. So this is shift amount was specified as an immediate number. That means it comes to this format. It is this format. Now logical shift left by register. So it's not like always you should give this shift amount as the immediate number. So the shift amount can also be given in the register. So RM, so this is the register whose value that should be shifted. So what shifting you got to do? Logical shift left, and how much to do. And now I don't have the shift amount in the as immediate number. It is in the register RS. And similarly for logical shift right by immediate. So shift right by immediate, logical shift right with register, and then logical shift right, sorry, arithmetic shift right by immediate, and arithmetic shift right by register, and rotate right by immediate, rotate right by register, and then rotate right with extended, RM, RRX. Now what happens, this uses 32 bits. Okay, so this is what you got to write when you want to rotate along with the carry flag. Now how much to rotate, you can specify again it by using the immediate number or by using the register. Hope you people understood. Hello.
Yes, sir.
Okay. Now arithmetic instruction. Till now, till here you we had a discussion on the move instruction. So we had a detailed discussion on the move instruction. Now next is arithmetic instructions. Okay. Now, so the syntax of the arithmetic instruction also goes like this. Okay. So till here it is same as the move instruction, but move was taking one destination register and n we used to write. But arithmetic instruction, it is something like this. We have the destination register, we have the first source register and an n. So this n can be a second source register or it can be an immediate number. Okay, that is the reason we are writing it as n. So can you make both of them as the immediate numbers? No, not possible. So only one operand can be an immediate number, but the other operand should be there inside the register. Okay, so that is the reason. And this syntax, what is written here, clearly explains what should be what. So RD is a register, RN is the first source register. Okay, and n can be either a second source register or it can be an immediate number. Okay, now. So what the instruction? So instruction here, what I've written can take any one of this. Now ADC adds two 32-bit values and a carry. Okay. Now why it's called C? Because it adds along with the carry. So something like this. So it takes the value which is there inside the first source register Rn. It takes the value which is inside either the second source register or it may be an immediate number. And to that, it also adds the carry. So the content of the carry flag also gets added. Okay, so that is what is ADC, adding with the carry. Now add. So this is well known because all of us have used this add instruction till now. Okay, and we have written the programs also. Adds two 32-bit values. Now RD is equal to Rn plus n. So this n can be either an immediate number or a second source register. And one more thing is this RSB, reverse subtract operation or reverse subtract instruction. Okay, so reverse subtract of two 32-bit values. So when I write say RSB here, RSB, and these two are optional. So if I'm writing RD comma RN comma n, now what it will do, it is not going to subtract n from Rn. Instead, it is going to subtract Rn from n. So this is what it does. That is the reverse subtract operation. And then reverse subtract with carry. Okay, now what it does, so from n, the second operand, it subtracts the first operand and also subtracts the negation of the carry flag. Okay, so negation of the carry flag is also subtracted. So you can see minus not of carry flag. So carry flag is 0, it will subtract 1. If the carry flag is 1, it will subtract 0. Okay, and then SBC, subtract with carry to 32-bit values. Okay, again, so this is what reverse subtract, and this is the normal subtract. So subtracting the value of n from the first source register and also subtract the negation of the carry flag. And sub is one which we have already understood. Okay, subtracts the normal subtraction, which is going to do Rn minus n. So subtract the second operand from the first operand. Okay, and store the result in the destination. Okay, people understood with this all these instructions? Hello.
Yes, sir.
Okay. Now we have the example. I think it's not necessary to go in detail with this example because all of you know this. Okay. Now what we are doing here, yeah, R1 is 2, R2 is 1 is the value taken, R0 is 0, and R0 I'm making as the destination register. 2 minus 1 I'm doing, the result is 1. Okay, result is 1. So example, and reverse subtract, and this is what you got to understand here. Okay, see now, so R0 is this 0. In R1 I have 77. Now I'm trying to do the reverse subtract operation. R0 is my destination. What is that I'm trying to do from R1? So this is R1. I'm trying to subtract 0 from 0 minus 77. I'm trying to do. When I try to do 0 minus 77, I should get a negative value, and this is a negative value. So because this f, how to write f 1 1 1, and the 31st position you got it as what 1. Now when I say this 0 0 minus 77, it comes in the backward direction. Now, what is the maximum address? Sorry, maximum value. What is the maximum value? What is the maximum value? F. What is the maximum value that you can write into the register?
F.
8 Fs. So 4, 5, 6, 7, 8 Fs. From this 8 Fs, you back count how many times? 77 times. How much you get? This. Hope you understood.
Yes, sir.
Okay. We'll stop here. So tomorrow I have a few more examples, and we're going to execute also. Many examples are there to execute and show you. So we'll stop at this point. I'll just please remember this. So we were in example 2 of arithmetic instructions. Please remember this slide. Otherwise, I'll forget. Okay. Let me mark attendance now. So if you have any doubts, so please ask me. While I'm taking the attendance, also you can call if you have any doubts, and you can discuss with me. So before taking the attendance, I'll stop recording.